Okay, so let's start. So today's lecture is really very important. Do your best to focus with me. So last time, or in this chapter, as I told you last time, in this chapter, I'm going to explain if you have an EC circuit, how can you analyze EC circuits? Okay? We didn't do that comparing to the previous chapters. We didn't do that. What do you mean by AC circuit? It means the sources we have are actually cosine. Okay, so sinusoidal in general. Okay, so here our standard form should be cosine. As I told you last time, the way we will do it is I'm going to take the circuit we have in the time domain, and then I'm going to convert this circuit to what we call complex domain, where all numbers here are in complex numbers, okay? And then after that, you need to solve here in the complex domain. It's going to be exactly similar to what we did before, okay? So for example, here in this conversion, Vm of cosine omega t plus theta, the way you have to convert this one, Vm, okay? And then we take only theta and we remove omega t. Okay? We remove omega t just to make the calculation easier, but there should be omega t, but we just remove to make the calculation easier. But there is no problem because when I go back, when I go back to the complex domain, to the time domain, I'm gonna add it back. Okay? There is no need to just keep omega t in the calculations. Okay, as long as I will add it back. This is because if this one is sinusoidal, okay, so for sure every voltage, every current, everywhere, also it will be sinusoidal with the same frequency. That's what you should understand. Okay, so if the input here has a certain frequency, if you calculate the voltage of the current everywhere, it will be the same frequency. What may change is the angle or amplitude. You got what I'm saying? So if I calculate the voltage here, for sure it will be the same frequency, but it will be different. Angle may be different or amplitude. Okay? Anyway, so here that's why if you have a voltage source this way, Vm of cosine omega theta is going to be a complex number this way. Okay? Also, last time I told you, if you have a resistance R, I'm gonna convert it to an impedance, okay? It's gonna be also R. So Z1 here is R. Okay, very easy. R is R, that's it, very easy. However, if you have here an inductor with inductance L, as we see here, this will be replaced by an impedance. Again, impedance means like a resistor, because as I told you before, similar when we had before V equal IR. It's the same thing. V is equal to IZ, but this one in the time domain. Whatever Z is, okay? V is equal IZ. So we're gonna treat this impedance like a resistor as we did before. Okay? So you can imagine, you can see this circuit as you have resistance, and you can solve it similar to what we did before. The only difference is the numbers we have here, all of them are complex domains. This is the only difficulty. But for circuit, I'm not going to teach any theorem, anything in circuit, because we're going to use everything we used before, okay, as you will see. But anyway, so here, this R should be like an impedance with this value is R. For this one, for the inductor, Z2 here is actually J omega L. It's a complex number, J omega L, okay? You have L here, okay? You have omega here because I told you the whole circuit has the same omega, okay? And the impedance here, Z3, is actually 1 over J omega C. See here, this is omega. And or, you know, if I multiply J over J here, J over J, so it's going to be the same if it is minus J omega C. Is that okay? After that, you solve it similar to what we did before. You can use, as you will see, I have too many examples, okay? I will do exactly everything in same thing as I'm doing here in all examples, okay? But we are going to use everything we used before, like Kirchhoff current law, Kirchhoff voltage law, everything, okay? And then after that, after you solve and then you get subcurrent anywhere. For example, this is I1, whatever. So after I get subcurrent, this way is a complex number. You have to convert it back to the time domain. So I'm teaching here, this is for any current, for voltage, for anything. How can you convert it? Okay. The 3 you have here, this is the amplitude, it has to be here. The angle you have here, this is theta, and then you need to add omega t. Is that okay? Again, I will I'm gonna solve many examples. All of them I will do the same thing as I'm doing it here. Okay, but there are several things I wanna highlight here. Number one, you can see in case of a resistance, the magnitude of the resistance does not depend on the frequency, right? So it's almost the same frequency. However, if you look at the inductor, this is for the inductor here, you can see the impedance depends on the frequency. You get what I'm saying? That means by changing the frequency, the circuit will be different. In the value of the impedance will be different. That's what I want to say. Okay. Same thing here. This here, the value of this impedance also depends on the frequency. And you can tell from here, as we increase omega or as we increase the frequency, the Z of L of the inductor is gonna increase, but Z of capacitor is gonna go down. Okay? And I wanna link what I did right now with what I told you before. When the input is DC, that's what I said before, when the input is DC, conductor becomes a short circuit, inductor becomes short circuit, a capacitor becomes open circuit. Okay, still I can support what this fact from the equation we have here, because in case of DC, omega is equal to 0, frequency is equal to 0 in case of DC. So if you plug in here 0, you can find here ZL equal to 0, okay, which is short circuit, as we said explained before. You can see Z of the capacitor equal to infinity, okay. Because 1/0 is infinity, which is actually open circuit, and I explained to you. Any questions? So there is something important here also I want to bring to your attention. That is, I told you here, because the whole circuit depends on the omega you have here. So let me ask you a question. And that's what I'm going to address later. And also I told you, if you have a frequency omega, so here omega, anywhere in the circuit, when you calculate current or voltage, it can also have the same frequency. That's what I say. So what if you have another source here, for example, the circuit has 2 sources, and the 2 sources, for example, have different omega. So here, for example, omega 1, now omega 2. You get what I'm saying? So for sure, as I will tell you later, I said, or the easiest way to do it is just do superposition. If I do superposition, I'm gonna have 2 circuits. Every circuit has only 1 omega. Okay. But anyway, most of the time we should have, or I just want to bring it to your attention, the whole circuit should have the same omega. So if you have a situation where I have 2 sources and they have different omega, in this case I have to do superposition. Once I do superposition, as you will see in the example, I will have 2 circuits. Every circuit has only 1 omega. Okay. But again, why you are doing that? Simply because we didn't do that in case of DC before, but that's simply because by changing omega, impedance changes. Okay. Everything changes. Okay, but I will explain it later for sure. But I just want to bring your attention here. If you have an impedance, for example, J200, if you find something like that, this is for sure it's inductance. But if you find negative J200, so you can tell if you have impedance, and I don't know if this is inductor or capacitor, you can tell, because here, if J is positive, so it has to be inductor, it has to be a capacitor. If it is just a real number, okay, without any J, so it is resistance. As you will see, as I told you before, if you have two impedance, you can add them together if they are series or if they are parallel. Okay, so if I have something here and I don't know what I have here, but it has a real part of 4 plus J200. So this is actually equivalent to a resistance of 4, and here this one is J omega L. Okay, for sure, omega L is equal to 100. From here, if you know omega, you can easily calculate L here. Okay, same thing here. If you have 4 minus this one here, so this will equivalent to series, okay? It's two a resistance and capacitor in series, okay? Okay, this is one more thing also I accepted last time. Yeah, in this slide here. Yeah, this is the I explained here in these slides here, and then I summarize. So here in this slide, I told you in case of a resistor, if you look at the current, there is one thing also I want to tell you about, guys. Usually we are going to use lowercase, as you see here, when it is in the time domain, but if it is in the complex domain, usually I will use uppercase, as you see here. Okay, so instead of V here lowercase, it will be something like that. And instead of I this way in time domain, it will be I this way. Okay? But I want to bring your attention here, or I want to clarify here, if it is a resistance, if you look at the angle here between I and V, they have the same angle, okay? In case of an resistance, does not change the angle, okay? That means in exams, in anything, when you calculate the voltage across a resistance and you calculate a current, they should have the same angle, okay? Omega T plus 20, omega T plus 20, for example, okay? However, in case of inductor, actually I is behind by 90. In other words, as we see here, if this is the angle of the voltage, it should be equal to the angle of the current plus 90. Okay, so there is a 90 difference. And again, this 90 difference came from here, because we differentiate, because the relation between voltage and current is differentiation. So when you differentiate, this is because of this differentiation, you are going to make 90 difference. Okay. This is again, this is the voltage and the current across an inductor. Here again, here actually the I is actually 90 ahead. Okay, so that means theta V should equal theta I minus 90. Okay, simply because we integrate here. So we integrate this one because of this integration. This is why they make a difference in the angle. Okay, so now I think we are ready. As I told you before, once you have impedance this way, you can do everything we did before. So here, for example, as explained before, if you have something like that, you have Z1 and Z2, you can see Z1 and Z2 like two resistors, okay? If you have two resistors in series, okay, how can you get the equivalent resistance? I just add them together. We will do the same thing. Okay, so if you have an inductor and then a capacitor in series, okay, so I'm gonna add this one to this one. I'm gonna impedance to this. That's it. And by this way, I will get the equivalent impedance. Exactly same thing as we did before. Same thing here. If they are in parallel, same thing as we did before. 1 over Z equivalent equal 1 over Z1 plus 1 over Z2. Okay, nothing is new. But the only difference, we are gonna use complex number, but this is similar to what we did before. Okay. Same thing for voltage division. If you have a voltage here, voltage division, and I wanna get the voltage here, for example, across V2 here. So I have to multiply V by this by Z2, as you see here, divided by the summation. Same thing as we did before. Okay. For the current, still I can use current division. Everything as we did before. For example, if I want to get the current here, I'm going to multiply this current by Z2 divided by the summation, Z1 plus Z2. Okay, again, nothing is new. The only difference is all these numbers are going to be complex numbers. This is the only difficulty you have here. But so that's why I encourage you to find a calculator, or find, if you already use calculator, as a way to do this complex number in a nice way. This will save. You are going to save 70% of the work here, because again, nothing here is new regarding circuit. It's just the only difficulty, because everything will be here with complex domain. Okay? Then let's see one example. I just skipped it here. This is not an example. I just want to explain to you here, or I just want to show you here why it may be easier, why it is easier to do the calculation in the complex domain than working on the time domain. Okay, because if you work on the time domain, it's gonna be, for example, here I show you here. Yeah, here I want to do something very simple. I want to subtract voltage from voltage. Very simple. Okay. So if I want to do something like that, you subtract voltage from voltage here in the time domain, it will be difficult. Why? Because they have different theta. They are not the same theta. If they are the same theta, it would be easy. You just subtract the amplitude the same. But here, because it's a different theta, so here you have to do a lot of manipulation, algebra manipulation, for example, using something like that. Cosine alpha plus beta equal to cosine alpha, cosine beta, sine alpha, sine beta. Anyway, so you can see here, it will be too complicated if you just do something simple like subtraction in time domain. That's why it will be much easier. For example, if I want to do this subtraction in the complex domain, so what you have to do here is you have to convert the first one to the complex domain. To do the conversion, I'm going to take root 5, I'm going to take 15, and no omega t. Same thing here, this one is 20, this one minus 20. If you have a calculator, you can do this calculation immediately, you can just get the answer. So it's very easy. If you don't, so you need to convert, because I said in addition or subtraction, it's easier to work with the rectangular form, the polar. So here, I can convert this one here to a rectangular form, and then I'm going to subtract real from real, imaginary from imaginary, and then this is the answer. Okay? This is the point. Once I get this answer here, or once I get some subtraction, if I want to transfer it again to the time domain, okay, so 15, I will take 15. This is theta, the angle, but I need to put back omega t. Any questions here? Now I will start to have many examples here, guys. How many examples I have here? So many examples, actually, from 6 until many examples here. So I have many examples. I will teach them. Again, as I told you, nothing here is new. So here, yeah, let's start the first example here. Yeah. In this example, as you see here, guys, this is the time domain. I have a voltage source. I give you the voltage source as you see here. The angle is 0. Okay. I give you L. I give you R. As you see here. First thing I'm asking you to do, I am asking you to redraw the circuit in complex domain. Okay. So when I redraw the circuit in the complex domain, as I told you, this one here, yeah. So here, this voltage source, which is here in the time domain. How I have to calculate it in the complex domain. It should be 1000 and angle 0. Remove omega t. Okay, angle 0. So that's it. So this is Vs. Okay. For R will be the same R, no difference. So this is R. Okay. For the impedance here, this impedance here, okay, is actually J omega L. J omega L. I give you L here, and I give you L here, and omega is here. Okay. So you need to multiply. L, which is 2, multiplied by omega, which is 100, so it's actually J200. So this should be the circuit in the complex domain. Okay. So I have already this source in the complex domain. I have R in the complex domain. I have the impedance here in the complex domain. Is that any questions? Okay. Now I'm asking you, can you give me the total impedance here? Total impedance. Okay. That's very easy because you are in series. They are series. Imagine you have here one impedance plus one impedance. So they are in series. So all what I have to do, because it's in series, I'm going to add them together. So here, as you see, Z should equal R or G omega L. Okay, that's it. And nothing else I can do, because I add real number to real number, complex number to complex. That's it. I'm done here. Okay, if you need it in the polar form, you need to convert this one from rectangular to polar if you need it. Is that okay? Because they are series, I just added them together. Next question here, I'm asking you to give me the voltage and R. The voltage here across, I need the across the inductor, and I need the current R. Okay. Can anybody tell me how I can get I? How I can get the current here? I. If you have a source and another resistance, total resistance. I already calculated the total resistance here. What is R? You have source and total resistance. Just to divide the voltage source by the total resistance. That's it. Okay. So here, if you want to get I, just I already know the total resistance. Okay. I'm using the word resistant. It shouldn't be resistant, but I want you to remember what we did in the DC, right? Here is the total impedance. Okay. Anyway, so here PS, the voltage source divided by Z. That's it. So PS here is a complex domain divided by Z. Yeah. That's it. Once you do that, I thought it's a current with a complex domain. Yeah. Once you know the current here, once you know the current, can you calculate the voltage across this resistance? Again, it's not resistance. Across this impedance, if I know the current, can I calculate the voltage across this impedance, which you can see it like a resistance as we did before? Okay, how can you do it? You know the current, you know the impedance or the resistance. Can you calculate the voltage across the resistance? Ohm's law. So all what you have to do here, just as you see here, the voltage is equal I times the impedance. That's it. So here, so now this is a complex number. I have to multiply it by another complex number here. Again, if you have calculators that can do these calculations, this is the only difficult here. It's just how can you multiply, divide these numbers in complex domains. So if you have calculators that can do that, everything will be okay. If you don't, you need to know how to do it. Okay, so here, this one here, as I told you before, in case of multiplication, it will be easier if you can do multiplication for division in polar form. So it's easier to convert this one to polar form. Okay, to convert this one to polar form, it's going to be 200, and in case of J, not 90. Okay, and then when you multiply, I'm going to multiply the magnitude by the magnitude, and then I'm going to add the two angles together. That's it. So now I have the voltage, I have the current here, and I have the voltage here. This is, okay. Is that it? No, you are not done yet. Okay, you need to convert it back to the time domain. You need to convert them back to the time domain. Don't forget to do that in the exam. In exams, in anything, don't forget to do that. Don't leave the number in the complex domain. You have to convert it back to the time domain. So to convert this one to the time domain, number one, this is the amplitude, 3.53. Okay. It will be cosine, always cosine, okay? And then here you need to add omega t, and then this is the angle. Very easy. Same thing here. If I want to convert this is the amplitude, magnitude here is the amplitude here. Okay? Oh, you need to add omega t, and then you need to add the amplitude. Any questions? Again, nothing here is new. The only difficulty is how can you do calculations in complex domain. If everything else is the same. One more thing here we can. That's why I copy this example from the textbook, because this problem is somehow very close to this problem. But we can solve this problem in a different way. For example, if I ask you to give me the voltage here, and you know this voltage, so I give you this voltage, but I need to know the voltage here. Can I use voltage division? You know what I'm saying? So instead, so now to solve this problem, similar to what we did before, there are two ways. One way, as I did here, you can get the total impedance, and then you need to divide V by the total impedance. Once you have I, you just multiply I by the Z here, that's it, you are done. Okay? Especially in this example, because I asked you to give me the current and the voltage. But if I ask you to give me only the voltage, it may be easier to use voltage division than doing this one, because here you need to do two steps. If I ask you only to find the voltage, okay? So that's why I can solve this one. I can find the voltage here directly. If I want to solve this one, I can solve it in a different way. I can find the voltage here directly using voltage division. So I'm gonna multiply the source by this impedance divided by the summation of these two impedances. Okay. And once I do that, I will define the voltage here. And then you can divide this voltage by this impedance here to get the current. This is another way. Okay. And I think that's what they did here in this example. So in this example here, you have here 7.28, as you see here, angle 77. This is omega t. I removed omega t. Here, this one should be J omega L. Omega is 4, so that would be 4 times 0.54. It should give you J omega A here. Okay. And now, if you want to get the voltage here, I'm gonna multiply this source by this one here, by the impedance here, divided by the summation of these two. I think that's what I did here. So here, that's what I did. This is the voltage, this is the summation, this is the impedance of the inductor. Okay. Now we are gonna come. Now we are gonna come to the nice part. You need to convert everything here to the complex to a polar because it's easier. Okay, and then once you do that, you can multiplication or if you are here again multiplication, you are multiplying magnitude by magnitude divided by magnitude as you see here. For angle you add. I'm multiplying these two numbers together, so I'm gonna add this angle to this angle minus this angle. Okay? So this is the result. Once I have this result, can I bring it back to the time domain? Yes. This magnitude is the amplitude. Omega t, don't forget it, I need to add it, and this is the angle. Okay. Again, the reason I put this example here from the textbook because it's very close to this problem, but we use a different approach here than what used. Okay, guys, any question? You need to practice. On how can you do mathematical operation using complex numbers. Yes.
On this example, you're finding
This one looks
yeah,
like
going from J200. Where does the 200 angle line?
sorry, your question again. What is the 200 and
Where's the angle 90? You're 30.
you need use this one?
Yeah, right below that J.
Yeah.
That would be
200.
Yeah.
When you convert it, you get 190.
Where is the 90 angle line?
That's a very good question because if you want to convert it, it has to be G200 is actually 0 plus G200. Okay, so if you want to find this angle, it has to be 10, the inverse of 10 of B divided by A, right? B here is 200, A is 0. So it should be inverse 10 of infinity. Okay, and this is one of the special cases I put them here. Yeah. So for example, if you have here J, yeah, if you have J here, because this is gonna be, you need to calculate the inverse of 10 of infinity. So this is one of the special cases you have here. One or J, you got to say. Any other question? Good. Because you need to do this calculation. Look what I'm saying. You need, again, my opinion, my advice is the worst thing you can do, just to read the slides. This is the worst thing. You need to solve it by yourself. Because when you read the slides, if I give you one of these problems, you are not going to, I'm sure you are not going to be able to do it. Okay? Especially for the calculations. Okay? So now I'm gonna come to another. Yeah, let's. There is something here I forget to tell you. I told you, okay. I told you here the angle for the. If you look at the voltage and the current here, I found. Look here, guys. The voltage and the current here for the inductor. I told you the difference in the angle is 90, which is true here. You can see. You can see theta V equals theta I, theta V, which is 45. Equals theta I minus plus 90. Okay, I told you about the relation between I and V for the inductor and for the capacitor. I just want to confirm it here. Okay? Let's have another example. This is a very simple example. I have a current source. This current source is actually 10 cosine omega t plus 0. This is a current source you have. It's AC current source. Okay, and then we have here a resistor. We have here a capacitor. Again, the thing you have to do, you have to draw the circuit in the complex domain. Okay, so to draw in the complex domain, number one, you have this source. I have to convert this source to the complex domain, which is very easy. With this amplitude is 10 and it is 0. That's it. Any problem here to convert this one from the time domain to the complex domain, very easy. For R will be the same R. So here R is 1 ohm, so it's gonna stay 1 ohm here. Okay. For this one, now I need to calculate the impedance of the capacitor, which is 1 over J omega C. 1 over J omega C. Okay. So here, as you see, 1 over J omega. What is omega? You can get omega from here, right? 100 here. Okay. Omega C. Is it C? C the capacitance. What is the capacitance? The capacitance. Yeah, sorry, this is the capacitance is here, 10 millifarad. This is the capacitance, and this is the omega is here. Okay. So once you do the calculation, you find it is 1 over J, which is equal to negative J1, or sometimes we remove the 1, which is the negative J. Okay. That's it. So now you have here impedance, which is 1 ohm. You have another impedance here, which is negative J. Okay, the impedance you have here, and then you have this current in time domain. Sorry, complex. Any question? Second question, again, nothing is new. I'm just if you don't know how to use voltage, anything I taught before, I'm repeating it now. Okay, regarding voltage division, current division, everything. Okay, so now I'm asking you, give me the total impedance. Okay, similar to what we did before, Z here should equal R in parallel with ZC. Okay, as we did before, which is should Z here should equal. You need to multiply them together, and then in case of two, if there are only two resistors, okay, you need to multiply them together and then add them here. Okay, if they are more than that, so you have 1 over R equivalent should equal 1 over R1 plus 1 over R2 plus 1 over R3 and repeat. Anyway, so now I'm going to do some multiplication here. I'm going to have this one here, negative G1, 1 minus G1, okay, and then after that. You can do some manipulation, like you multiply here by G and here by J, you get something like that, and then you can convert. This is something you need to practice. How can you do this calculation? Okay, this is the only difficult part here. So, and then you need to convert this one to this one here, okay, and then this angle I can bring it out, it has to be minus, okay, and the 1 over the square root of 2 is this value. Okay, this is the equivalent resistance. Again, this equivalent resistance in you don't need to convert it, okay? Unless I ask you, but anyway, this is the total. This is the okay, sorry. So this is the total impedance you have here. You can also, if you need, you can calculate what we call admittance. Admittance like conductance before, if you remember, which is 1 over the impedance. Okay. So here I calculated Z. So 1 over Z should give you the this value, this would give you the admittance, okay? Or you can say the total admittance equal, you can remove this one, it's just another way. The total admittance means 1 over R. So what is the admittance of R? 1 over R. What is the admittance of this one? ZC, 1 over ZC. Okay? So I can say 1 over the total, 1 over the Z equivalent, which is Y, the total admittance equal 1 over R, which is Y, 1 over ZC. What else here? Here I'm asking you after that, give me, find the voltage here. I want to find this voltage here, okay? Also, I want to find IC and IR. Any clue how can we do it? So if I want to, let's start how I can find the voltage here. The voltage, because the voltage here is the same voltage here, the same voltage here, because all of them are in parallel. How I can find the voltage? If you already know the equivalent Z, how can you find the voltage? Yes. Yeah, so let me, for example, go here. If you have a resistance here, another resistance here, okay, and I have a current source, this is one I find the voltage here. So as we did before, I can get the equivalent of this one, equivalent. So here are equivalent, and then I have a source here, okay, and then I multiply I times R equivalent, give you the voltage here. And because this may be the part you need to understand, because this is equivalent to this one, the current here will be the same, like the current going into this two. Also, the voltage here will be the same voltage because it's equivalent. Otherwise, not equivalent. This is the meaning of word equivalent. Equivalent means it's gonna give you the same voltage, the same current. You got what I'm saying? That's why the voltage source here will be the same like the voltage source. Exactly the same thing we can do here. I can multiply, if I multiply I by the total Z, as we see here, by this way I can get the equivalent voltage. The voltage across the voltage here, or it's which is the same voltage across the R equivalent. Here I multiply Z times IS, okay, and then I got the voltage, okay. If you already know the voltage here, if you know the voltage, okay, can you get this current and can you get this current? The answer is yes. Just to divide the voltage by R or divide the voltage by ZC. That's what I did here. So here what I did, IC should equal V divided by ZC because YC is 1 over ZC. Okay. I did it here. I got the current here. When I get the current here, V divided by R. I got the current here. Or you can apply Kirchhoff current law. I'm repeating the course again, by the way. So you can apply Kirchhoff current law if you already know. If you already know the total current here and you know IC, easily you can get IR. If you know IR, you can get IC because it's still similar to what we did before. IR plus IC equal R. Makes sense? Also, I want you to notice here the relation between, look here guys, look at the angle of the voltage, which is here, with the angle of the current in the resistance with here. It's the same angle, right? Same angle. But if you look at the angle here in IC at this angle, okay, you will find there is a difference of 90. Okay, I think you need to add 90 to the. You need to subtract 90 from I to get V. So here you subtract 90 from here to get this. The relation, I told you there is a relation always between the voltage and the current in case of inductor and also in case of current. Any questions? Okay. Once you have these numbers, you can easily convert to the time domain. So here you can see here 7.07, which is here, okay. And then omega t plus theta. Theta is here. Okay. Same thing here, 7.07, which is here. Omega t plus theta. Theta is here. Same thing here. You can see the magnitude is the same. You know why? Because the resistance is 1. So we divide by 1, it's the same. Same thing here. This one is 1J. Okay? Just by accident, that's why all of them are the same. Because you divide by 1. Any questions? Yeah, let's go to look at this example here from the textbook. You have here an inductor, you have here a capacitor, you have here a resistor, you have VS here. This is VS, it's given to you. Here, when the input of the circuit is determined V of T. I want to find the voltage here. I want to find the voltage across this one. Okay. How can you find? So this example is exactly similar to this example, but I added one inductor here. So this example, no, but also this one, sorry, has a voltage source. Okay. But anyway, I want to find the voltage here. Okay. To solve these problems, there are different ways to do it. One way to do it, similar to what I did here, you can calculate the total impedance. The total impedance, these two are in parallel and this one series. Is that okay? You can calculate the total impedance. Okay, once you calculate the total impedance here, you can divide VS by the total impedance to get I, this current here. Okay. Once you have I, it's easy now. You can use voltage division. Once you have I here, you can, I know I here, you can actually multiply by the total impedance of these two, okay, to calculate the voltage across these two resistors, okay, to these two impedance. But I think he did it here, I think it's the same way, but, so let's see how it was done here with this book, okay. So number one, I have to calculate the impedance of this one, which is easy, 1 over G omega C, okay. And then here, you need to calculate the impedance of this one, which is J omega L. Omega is here, L is given, C is given. So now I can calculate the impedance here and the impedance here as well. So this is the circuit in the complex domain. Okay. Then after that, BL here. Yeah. So as I told you, yeah, this is it's 50. Yeah. So here VL, the voltage here, yeah, VL here, which is the voltage here. The voltage here, voltage drop here is I. Here we have current here I times the impedance here. Okay, that's what I mean. So the impedance here is actually 50 J. Okay, if I'm 50 J times I should give you the voltage drop here. So VL equal J 50 R. Okay, and now the voltage here, next one here is IC. IC should equal the current here, IC should equal the voltage here divided by this impedance. Okay, V of W, which is the voltage here at this point, that's what I need to find, divided by this impedance here. Okay, same thing, the current here. So what I did here right now, guys, I calculated this current. Okay, I find this current as a function in VL. Okay, here. VL here, and then I found this current here. This current here is actually the voltage here divided by this impedance. The current here is the voltage divided by this impedance. That's what I did with these two. And the total current which is coming here is actually equal to this current plus this current here. This is Kirchhoff current law. Okay. So once I find the current through the capacitor, the current through the resistor, I can add them together. So this current is still function in V. I don't know V yet. Okay, but actually, so here now I can apply Kirchhoff voltage law. If I apply Kirchhoff voltage law here, guys, here, okay. So this source should be negative should be equal to this voltage plus the voltage I have here, or so this voltage plus this voltage should equal to this voltage. Okay, and this is so here. This is the source here, okay, should equal to the voltage here plus the voltage here. Okay? So this is the voltage I have here, and this is the voltage I have here. Okay. Now, all what he did here, he just tried to have an equation that has only one unknown, which is VW. And that's what happened here. Now I'm going to replace the total I with this part here, so that now I will have equation. This equation has only VW here. Okay. So after you do the calculations here, this is the result. Here you read this one here, and then you can divide. So you have equation that has only voltage here. You have equation that has this voltage here. Okay? How can you get it? Okay, I'm gonna say it again. If you apply Kirchhoff voltage law here, so this source, okay, negative plus voltage drop here plus the voltage here. That's what I want to make equation that has only this voltage. Okay, should equal to 0. Okay. So now the current here, the problem here, the voltage here, okay, in the inductor is actually current times the impedance. I have the impedance, but I don't know the current. But this current is actually the summation of this current and this current. Okay, and this current can be a function in V. That's what I did here. So you see, this is the total current equal IC plus IR. So this one actually only in V. So again, first I apply Kirchhoff current law, then I apply Kirchhoff voltage law, and then I make equation that has only one unknown. V W, I calculate it. That's one way to do it. There is another way. As I told you, you can calculate the total impedance. You can calculate the total impedance, as I told you, and then you can divide Vs by the total impedance. By this way, you can get the current, IT, this current. Okay? Once you have this current, I can multiply it by this impedance here, by the equivalent impedance of these two. Now you can get the voltage. Any questions? You have many examples. The slides themselves already have a lot of examples. I also took some examples from the textbook as you see. Now, Same thing, you can still apply node voltage, nodal analysis, you can apply it, mesh analysis, still you can do it, okay? Stephen in Norton, I know you like Stephen in Norton, that's why we will do it also. Also, you can have some kind of independent sources. Again, same thing as we did before. So here, so let's do it here first. First one here. Yeah. So I give you a circuit like this one here. I want to apply node voltage. Okay. So here, as you know, in node voltage, at every node I have is gonna be unknown. So here I need to find VA and VB. This is how node voltage. So here I need to make equation to find VA and VB. So I have two unknowns here, VA and VB. Okay. But for sure, I don't need to say if you have the circuit here in the time domain, you have to convert it to complex domain. This is the first thing you have to do. Okay. So if this is the current here, I can convert to the time domain this way. Now, if you have here for this inductor, that has to be J omega L, it has to be this way. Okay. For the here for this one here, the capacitance here, the impedance of the capacitance 1 over J omega C this way. Okay, so and the resistance will be the same. Okay, so number one, you have to convert the circuit from the time domain to the complex. So this is number one. Number two, you need to find, and I need to apply node voltage in order to be able to get VA and VB, VA and VB. You know how to make it? Yes. You don't have, I need to apply Kirchhoff current law here, so I already know this IS, okay? And then this current IS should equal to this current plus this current. Same thing here, this current should equal to this current plus this current. And now I need two equations. In complex domain, and these two equations have two unknowns, V and V. I need to solve them to get V and V. Okay? So the first equation, as you know, this current here, the total current IS should equal to the current here, which is VA minus 0, divided by the impedance here, as we see. Here, VA minus VB divided by R1. Okay. So now I'm gonna do just mathematical manipulation. At the end, I will get this equation. So this is the first equation I can get in VA and VB. First equation. Okay. What's really important is also, guys, even if you don't know, even you struggle in the calculation, show me the steps. I agree with that, okay? But if you don't even show me how you try to solve this one, you will not be able to solve. Okay, at least tell me, okay, if I was able to solve this one, okay, I can do the next step, and then show me how can you proceed if you can calculate. You understand what I'm saying? Because even if you show, at least you can show me that you already know how to solve it, but you struggle in the calculation, which is okay. So I give you partial marks here. Okay. So here, same thing. I will repeat everything here for VB. I need to find the current here should equal this current plus this current here. Okay, using this equation, Kirchhoff current law. And now, here again, I will have another equation here that has VA and VB this way. Okay? I need to solve these two equations. So how can we solve these two equations? Very simple. I need to find one variable here. I put it at one side, everything else on the other side. Okay. And then once you have this variable, you can, or this unknown, you can plug it in the second one. Okay. So that's what I did here. So if you see what I did here. Yeah, here from equation number 2, for example, you need to select which one is easier for you. So is that easier for you to get VA here or VB, whatever? So you need to see what's easier. So here, for some reason, I try to work on the second equation here. I want to separate VA. So I'm going to bring this one to the other side, and then I'm going to divide it by minus G. Yeah, that's what I did here. Okay. So after I do the calculation, you can see VA should equal 3 minus G to VB. Okay. Then I can take this VA of plugging in the first equation here. Okay. To have one equation in one unknown, which is VB. Okay. Yeah. So I took it. You can see the difference. This is only different about the calculation, but somehow complex calculation. Okay. That's why I will consider this. If I bring you a circuit, I will make sure its calculation are not going to be complex. Okay? But this is how it is. Okay. After that, I'm going to have only one unknown here, VB. I got VB this way. Once you have VB here, you need to plug in any one of the two equations you had before to calculate VA. Once you have VA, VB, you are done. So here I have VA and VB. So now this is VA and VB, but they are in the complex domain. You can convert them from the complex domain to the time domain. So give this one 87.61, 87.61. You need to add omega t here, and the angle is here. This one 24.27 is here, omega t, and the angle is here. Okay, guys? That's it. Nothing else here. Let's see. Any questions? Okay. So next one here, also this one example for mesh current. Yeah. So here, and also we have here a source, independent source, dependent source as you see here. So this dependent source is 3I. So 3 times, this is a voltage source. The value of this source, the voltage source is 3 times I, and this is I is here. Okay. So the complex domain is going to be 3I, okay, here, because this I here lowercase, I'm going to put it I in the complex domain. So this one should be 3I, as you see here. And because here I'm applying mesh here, and here, as you see in this loop, I equal to I1. So that's why I can say this one is I1. Again here, guys, similar to what we did before, you need to apply Kirchhoff voltage law here to find one equation. You need to apply Kirchhoff voltage here to find the second equation. Equation in what? In I1 and I2, because my unknowns here are I1 and I2. Is that okay? But I have a problem here. This one is I. Yes, you need to find the relation between I and I1 and I2 so that we need only 2 equations, not 3. In order to need only 2 equations instead of 3, this one here, I need to find the relation between this I here, and I1 and I2. Okay, which is actually what happened here. I is equal to I1. That's why I'm gonna have only. So let's see how can we do it. First of all, you need to do you need to convert it from the time domain to the voltage domain, which is very easy. So if you have this one here in the time domain, so in the complex domain, angle is 45, as you see here. Okay. If you want to get the impedance here, J omega L, as we see here. If you want to get the impedance here, 1 over J omega C, which is here. Okay. And then as you see here, I will apply Kirchhoff voltage law twice. I'm gonna apply exactly the same thing as we did before. I'm gonna apply Kirchhoff voltage law here. So this one here, I'm gonna apply Kirchhoff voltage law here. So it should be I1 times R. Here, this one, I1 minus I2 times J omega L, as we see here. All of that minus Vs equal to 0. Same thing, we can apply Kirchhoff voltage law here. It's the same way. I2, okay, times this impedance, it's here. Okay. I2 minus I1 times this impedance, as we did before, nothing is new. Okay. Plus this source here. This source is actually 3I1. Okay, now you have 2 equations. These 2 equations are in the complex domain, and they are in I1 and I2. You can find I1 and I2. Okay. So here I show you how to do that. So just I did here some simplification. I plug in the numbers, I did simplification. So here, this was the first equation we have. Same thing for the second equation. Yeah, so just you can enjoy the calculation here. Okay. So here once you have the 2 equations, yeah, these are the 2 equations I have. You need, similar to what we did before, for one equation you need to get I2 or I1 on one side, and then you have to plug in the other one. For example, here I found I2 equals this value, so I can plug it in the other equation. So I found I2 equal this one from one equation. I can plug in the second equation, but after finishing this calculation, I found I1 equal this value here, I2 equal this value here. Okay, so now I have I1 and I2 in the complex domain. Okay. Now, if I ask you to give me DC, I need the voltage. I need the voltage across the capacitor here. Okay. So this voltage should equal to I2 times the impedance of the capacitor, as you see here. So this is the impedance of the capacitor times I2. This is I2, and this is the impedance of the capacitor. Okay. If you just finish the calculation, it equals this value here. Okay. Same thing. If I need to find the voltage across the inductor here, the voltage across the inductor is actually I1 minus I2 times the impedance. I1 minus I2 times the impedance. You already have this impedance in complex domain. You have I1 I2. You can just do the calculation. This is the result you will get at the very end. Okay. Now, don't forget to convert. Don't forget to. Sometimes you lose marks without any need for that. So don't forget to, because this is the way I grade it. So for every step I put some points. So if you leave it in the complex domain and you forget to give it me in the time domain, you will lose some points. Okay, so and it's not difficult, but no. So here, if you have here, since it's the complex domain here, to convert it to the time domain here, as you see, I'm gonna take this one. Omega t, what is omega t? Yeah, omega t here plus this angle here. And then for VL, it's actually omega t plus this angle here. Okay. Again, if you look at the relation between current and voltage, it will be the same as I told you. Okay. So for example, here, the current here is actually I2. Okay. So if you see I2, what is I2? Yeah, I2 is here. Look at the relation, guys. I2 and the voltage of VC from here to here, it's 90. You subtract 90. Okay. If I subtract 90 from the current, I can get the voltage. Okay. Any question? Again, honestly, I don't see anything new here. I understand the calculation somehow complex somehow to do this calculation, but I'm sure you can try to find, if you can find, I'm not sure if you did something like that before using calculators or not. I think some of the calculators can handle these calculations. I have no idea, but anyway. Let's see the next circuit here. In this circuit, I want to find, let's see in this circuit. Okay. Yeah. Look here, guys. As I told you before, look, what is new in this example? What is new in this example that you see here? We have two sources. One of them with omega of 10 t. The other one is actually DC. So omega here is 0. You got what I'm saying? So I have two sources. You have to do the same thing if the even if the two sources are AC, but they have different omega. So you have to use superposition, because the way we calculate, the way we solve the circuits, we need to use only one omega. There should be only one value for omega. That's what I'm saying. That's why here, I give you this example. This one actually here is this 3A. 3A, this one is DC. As long as you don't see cosine or sine next to it, it is DC. So this one is DC and this one is AC. Okay. In order to solve this equation, I'm gonna use superposition. In superposition, I'm gonna put this one and then I remove this one. Remember how we remove this one? Open circuit. In the next, and then solve everything. The next circuit is I'm gonna keep this one and remove this one by short circuit. You got what I'm saying? And remember, in DC it's very easy, because if the current is DC, very easy. So this inductor becomes short circuit. This capacitor becomes open circuit. That's it. Okay. So let's start with the DC, because maybe an easy one. Okay. Yeah. Look here, guys. In case of I'm gonna keep the DC here, this current, and then I'm gonna cancel the other one by making short circuit. Okay. So this is the circuit. I think I'm asking you to give me the current here. We need to calculate the current here or voltage, whatever I ask you to do. Okay. So here because the input is DC, now the inductor is short circuit. The capacitor is open circuit. Now you can find anything you have. So if you look at this circuit, it's a very easy circuit. You look here, because R1 and R2 are parallel. R1 and R2 are parallel. So you have a current source and two parallel resistors, R1 and R2. Okay. So now easily you can use current division. So here you have I total here, okay, and these two are in parallel. If you read through the circuit, R1 and R2 are in parallel to each other. So if I want to calculate the current here, I'm gonna multiply IF by R1 divided by R1 plus R2, as you see here. If I want to calculate the current here in I1, so it should be IS times R2 divided by R2 plus R1. Okay. If I want to calculate the voltage here, which is the same voltage across R1, because all of this one node, 1 point, all of that is 1 point. So the voltage here across the capacitor here, or there was a capacitor, now there is no capacitor open circuit. But anyway, the voltage drop here is equal to the same voltage drop across R1, which is actually I1 times R1, or it's the same voltage across R2, which is I2 times R2. Okay, so whatever you can do, it's the same. You can multiply I2 times R2, or you can type R1 times R2. Anyway, so now I got the current and the voltage. Okay, the current here and the voltage here, because that now I need also to find the current here, but for the AC circuit, I need also to find the voltage for the AC circuit and then add them together. That as we did before. So as we did before, this circuit has a current source, it doesn't have the voltage source. I want to find the voltage here and the current here. Okay. So number one, you need to calculate them because of the DC source. Okay. I already found them here. I need to repeat again for the AC source. And then as this is a superposition. And then the total voltage should equal the voltage in DC plus the voltage, or because of the first source, because of the second source. Because of the first source, second source. That's it. You understand? So let's now go to the AC circuit, how the AC circuit looks like. So here is the AC circuit. I'm gonna remove, as you see here, this current source is gonna become open circuit. Current source becomes open, so this is how the circuit looks like. So the first thing you need to convert. You need to this circuit from the time domain to the complex domain. Okay. How any R is gonna stay R. Here this source, the source here it was 10 omega t, so the angle is 0. Okay. The impedance of this one is actually J omega A. The impedance of this one 1 over J omega C. Okay, guys. In tests and exams, every step you are doing, you are getting point for it. Okay, so at least if you don't know how to put it, at least you can convert it into a complex, so you will get point for that. You can understand? So now this is how the circuit looks like. So now I want to find the current here and I want to find the voltage here. Okay, I think the easiest way to do it, similar to what I did here. It's like you have here only one impedance, Z1. So Z1 actually is R1 plus J omega 1. I'm going to add these two together. Also, I'm going to have another impedance here, Z2. Z2 is actually this R2 in parallel with this impedance. Okay. If this is the case, you can easily find the voltage here. Okay. The voltage using voltage division. PS times Z2 divided by Z1 plus Z2. And once I find the voltage here, it's easy to get, because I want to find the voltage here and the current here. It's easy to put the current because this voltage I'm going to divide it by R2, get the current here. Again, Z2 is actually the equivalent of these two resistors. Z1 is the equivalent of these resistors. Okay? So that's what I did. Look in Z1. Z1 is the resistance because J omega, which is equal to this one. Z2 is actually the capacitor in parallel to R2. Okay. So here you multiply them and then you add them here. Then do the calculation, you get the Z2. Okay? Once I get Z2, once I get Z2, again, in exams, even if calculations are different, so show me the steps. You can, yeah, I will calculate Z1, then I will calculate Z2, at least, because if you don't write anything, I can't give you any points. But at least you show me you understand it, okay? You understand what you have to do, I will give you points for that, for sure. Yeah. So anyway, so now, how can you find the voltage here? This is voltage division. I'm gonna multiply Vs times Z2 times Z divided by Z1 plus Z2, as we see. V1 should equal Vs times Z2 divided by Z1 plus Z2. Okay. So here for sure, it would be easier if all of them are in the polar, all of them are no, sorry. Yeah, this one I have to convert this one to rectangular to add it to this one, and then I have to convert it back to polar, okay? Because multiplication and division in polar is easy. So when you go home, you need to enjoy this calculation. Make sure you can do this calculation using your calculator. Okay? Once I find the voltage here, okay, can you get the current here? Yes, the current. The voltage divided by R2. And this is very easy because here, this is just I'm going to divide 5 by 10. That's it. Because this 10 has only a real component. It does not have a complex number or imaginary. Sorry, it does not have an imaginary number. That's why 5 divided by 10. That's it. Okay. Now I got V1, I got I1. This is the voltage across the capacitor because of the AC source. This is the current here because of the AC source. Okay. Now I'm going to convert this into the time domain here. Okay. So here, this one is 5. I'm going to put 5 omega t minus 90. Here I here is half. This one is half omega t minus 90. Okay. So now I have V and I have voltage here and the current here for the AC circuit. And I already calculated V and I for the DC circuit. So I need to add both of them together. That's what I did. Okay. So this is the output. So if you look at the output, and this is very interesting, if you look at the output, you can find the output has two components. One component is DC without cosine or sine, and another component is a cosine. And this one DC plus EC. And you know, if you draw it how it looks like, because so for example, if you have a signal like this way, this is sine, or this is pure AC. If you have DC this way, okay, if you add them together, it will be something like that. Shift up or down, whatever. You got what I'm saying? Because we have DC component, you add a DC component to an AC component. So that's why if you look at the final equation, it has cosine something plus 10. Because this is this 10, because this is the impact of the DC source. And this is because of the AC source. When you add them together, this is how it should look like. It's going to be cosine shift. It can be up or down, depends on this number here, positive or negative. Any question? Okay, so now this is a time for Thevenin, your friend. Okay, so now I have this circuit here. I wanna calculate the Thevenin of this part here. I wanna calculate the Thevenin of this part here. Okay, so that's why after you calculate Thevenin here, it's gonna look like something like that here. Z Thevenin and V Thevenin. All of them are in the complex domain as well. Okay, so let's see how can I calculate Thevenin for this part. Okay, for this part is going to be replaced by Z Thevenin and V Thevenin. Okay, so here you can see Z1 is actually 1 plus J. So actually this one is a resistance plus inductor. This one here is negative G1. Negative G1. That means this one is a capacitor actually. Anyway, and I give you R here is actually 2, which this is not DC. Okay, this is AC. Big difference between if I tell you IS is 2 and stop. Big difference between this one and between saying this one is 2 and angle 0. You got what I'm saying? If there is angle 0 or whatever, so this is AC source, it's cosine. But when I say it's only 2, so this is DC. Okay? Because you may confuse, because of the angle 0, it should be DC. No, it's not DC, it's AC. Okay? But angle is 0. So it is actually 2 cosine omega t. That's how it looks like. But if without angle, just 2, so this is DC. Anyway, so similar to what we did before, we want to calculate Z7. To calculate Z7 for this part, as you know, any current source, I have to make it open circuit, as you see here. And then I need to see what resistance I see from here. You can see the resistance I'm seeing from here. If I look from here, because I want to calculate different for this part, so I want to look from here this way. You can find what resistance I will find here. Z1 in series with Z2. So Z1 plus Z2. That's what I did here. So Z7, as you see here, is actually Z1 plus Z2. Okay? I added Z together. The result is 1. That means the result is only a real number. Okay? So this is Z7. Now, for V7, I want to find the voltage drop here. I want to find the voltage drop here. Okay? The voltage drop here because there is no current in Z2, there is no current, okay? Current in here is equal to 0, there is no current, so the voltage drop here is the same like the voltage drop here. Okay? Or I can say here, that means all this current will come here, because there is no band here. All this current is gonna come here. Okay? So you can see here the voltage drop across Z1 is actually I times Z1. Plus the voltage drop here, which is 0, then I'm going to get the voltage drop. So I can say the voltage drop here is equal to the voltage drop here, which is 0, plus the voltage drop here. That's why I'm saying the voltage drop here is equal to the voltage drop here, because current here is 0. So all current here for IS is going to go through Z1 here, in this segment. Okay? So that's why this V7 should equal sorry, this is I times Z1. So I got it here. Okay? So now I have V7 and I have V7. Any questions? Yes, sure.
I'm confused how the 2 plus J2 equals the polar. Like how you do that.
Okay, that's a very good question. This one is equal? No, I only multiply it as well.
No, how, when you're converting rectangular to polar, converting.
This one here?
Yeah.
Okay. Look here. Number 1, the magnitude is the square root of 2 a squared plus b squared. Is that okay? Square root of a squared plus b squared. Square root of a squared plus b squared is actually square root of 8. 2.83, I think it should be square root of 8. Is that okay? Now for the angle should be inverse of 10 b divided by a. Okay? So it should be the inverse of 1, 45. B, this is b divided by a. So let me go to maybe I wanna let me go to the very beginning here. Yeah, look here. This is rectangular form. So whatever you have here, I'm gonna put it A, whatever you have here, I'm gonna put it B. Is that okay? So in order to calculate the magnitude, as you see here, is square root of a squared plus b squared. In order to calculate the angle, it has to be inverse of 10 b divided by a. B divided by a. But be careful here, because as I said, if A is positive, you have to use this one. If A is negative, you have to use this one here to get a correct angle. Okay. I think that's enough for today. So next time I will complete this example. So I hope any other question Tiffany here? Okay. Next time, this is the same thing, but we're gonna calculate Norton. I will give you more example next time. Okay. I finished the test 2. Okay. And we're gonna. I already posted. I sent you an email, and I posted the grades.